Okay, so good afternoon, everyone. Let's wait for 5 more minutes to see if other people join, and then we'll start. Okay, So let's begin. Welcome everyone. So this please make someone confirm that if I'm audible or if you can see the screen.
Yes, sir, you are audible and visible.
Okay, thank you. So again, welcome everyone. This is NOC24 W139 NPTEL tutorial session on microelectronics devices to circuits. The course instructor is Professor Sudev Das Gupta from IIT Roorkee. I am Debashish Nandi from IIT Kanpur. So this is week 10. So these are the prerequisites which you are already aware of. So this is week 10. So let us begin. So it is asked that in the first question that identify the transistors forming a current mirror circuit in the given op-amp topology. So if please confirm if this topology is visible, else I will just make it a little more bigger. Okay. I think it is better to have an enlarged version. So can you tell me what is this circuit? What is this basically? Can you comment? Uh, some of the blocks you are aware of, right? We have discussed in
Yes,
the
sir.
last session. So can you
Yes,
tell
sir.
me what is this?
In center, big block is differential amplifier.
So you meant to say this
In,
entire stuff is differential amplifier, right?
yes, sir.
Okay. And what about the bottom one?
Bottom,
What is that bottom side? What is there? So this you said that it is basically a differential amplifier. Differential amplifier where this is your input 1, this is your input 2, and this is your output. Fine.
yes, sir.
So is that all of the differential amplifier? And what about this stuff? Uh, what about this entire stuff? What is this thing?
Looking like current mirror.
Looking like not, it is actually a current mirror, right?
Yes, sir.
And why is this used? I have discussed this in the last class, and I have told you
To
that
take current, to take current,
to
connect
base
high.
basically in the small signal sense, looking at this point, you should see a infinite resistance, right? And the reason for that is whatever current is flowing in this path should flow, differential current should flow through this path. So you should have a open circuit, small signal open circuit, small signal OC. So that is done with ideal source, like if you connect a current source, right? So that current source is basically this one. This is how you have current sources in your IC, because what is happening, this is your off chip master current source. Okay, now you want to that is only one means master current source means you will only have access to one current source, because to make that you need so many things like band gap referencing and all. Okay, that takes huge amount of area, or some kind of LDO or something like that, low dropout amplifier or something like that. That takes huge area. Okay, if you see any design of low dropout amplifier, you will see that the W by L ratio is generally in millions. Okay, so now, so what is the way towards that? You have access to this port only. Okay, this is outside chip, this is outside your IC, outside IC. Now what do? You take that, connect a MOSFET and start mimicking the current sources. So that is called current mirroring. So wherever you require a current source, you just make sure that the W1 by L1 and here W2 by L2, if you need the same value of the current source, you keep this W1 by, for example, if this is also I0, then what do you need to do? You need to have your W1 by L1 has to be W2 by L2. Otherwise, by changing the ratio or the relative W by L between the master current source, the MOSFET connected to the master current source, and that to the connected at the current sink at the below of your differential pairs or wherever it is required, with that W by L ratios, we can tune the value of current what you are getting. Okay. So that is what is a differential pair. And what about the other stuff? What about this thing? What is this guy doing here? What does it look like, by the way?
I will like CMOS.
No, no, CMOS is fine, but what does it look like? Means it is a switch or an amplifier or an inverter. What does it look like?
Integrator.
Integrator? Why do you say? For the time being, ignore that this capacitance is not present. Okay, I'll talk about it later. For example, now don't think that there is a capacitance. So now what do you have? You have a op-amp. Let's say this is the differential amplifier. What you have? This is your V1, this is your V2, and this is the plus terminal, this is the minus terminal. So this is, and then you have connected a PMOS, right? So you have connected this to an input, and this is your, let's say, VDD, and you have connected a current source. It is this bottom thing is nothing but a current source, right? It is the same current mirror. You see that
Yes,
it
sir.
is nothing but a current source. So this is, let's say, the same current source I0. Okay, and this is your M10. So let's say this is your VO1. So what is your VO1? VO1 will be the gain of the first stage, the differential gain of the first stage times V1 minus V2. So that is the input signal at this point. So, and where are you taking the output? You are taking the output, let's say, at this point, VO2. So what will be your VO2? So what is this basically? So the question you have understood, right? I want to know what is this. Any comment, any observation?
So that is simple a MOSFET.
Yes, MOSFET, but MOSFET drain is connected to a current source. So let's say you have this, okay? So you have a current source here. So this is like I0. This is where you are applying your V in and you are taking your V out here. What is this? What is your V out? Can I write V out is minus GM R naught times V in?
Yes, sir.
Can I write that this is a common source amplifier?
Yes, sir.
How did I write that? Do you understood? Have you understood that this is a common source amplifier, this topology?
Yes, sir.
So for those who have not understood, in your small signal sense, this will go out and you have a R naught here, right? And this current is your GM times V in, and that flows through this R naught and gives you this voltage. So now what I have asked you that what is this? So you have same situation, but you have a current source connected like this, and it is a PMOS. So this is your VDD, this is your V in. So I asked you that what is your V out. So what will be your V out? Let's say this is your GMP. The transconductance is GMP and your R naught is R naught P. What is your V out? What is the
Yes,
source, by the way, in this case? This is gate, this is drain, and this is source. Is that okay?
source interchange. Source
Yes,
is
right.
above and drain is down.
So if you have seen this, that the source is the above one and the drain is the bottom one, then what will you do for small signal analysis? You will make this grounded. You will just open this. So doesn't it show the same thing with a PMOS? It is a PMOS common source amplifier, right?
Yes, sir.
So V out will be GMP times R naught P times your V in. Is that okay?
Yes, sir.
So have you do you see that this is nothing but your common source amplifier?
Yes, sir.
So now what is your overall circuit? Your overall circuit is you have a differential amplifier. This is your V1, this is your V2, and that is connected to a another common source amplifier, right? This is your V01 and you are having V02. Let's say this is having a gain of A2, and this is a gain of A1, or this is a gain of AD1, and that is connected to a gain of A2. So what is your overall gain? Your VO2 will be what? AD1 times A2 times V1 minus V2. Is that okay?
Yes, sir.
Because in your DC analysis, I can always open my capacitance, right?
Yes,
Because
sir.
at DC capacitance is open. Is that okay?
Yes, sir.
So do you see that this is nothing but a two-stage amplifier? This is your first stage and this is your second stage, okay? So this thing is called basically two-stage op-amp or two-stage differential pair, okay? So this is your first stage and this one is your second stage. Now, why this capacitance is included without going into the detailed analysis? So you have something like this. So let me just put it in this way. This is your R naught, and just let me use our conventional symbols that we have used, that we have been using. So this is your GMP, this is your V1, this is your plus, this is your minus. So this is your V1, this is V2. Let's say the first stage is happening some GM effective. So, and this is the R out of the first stage. So can you tell me where is that capacitance connected? C1. Let me just name the nodes. This is A, this is B, this is C, and this is D. Can you tell me between which two nodes the capacitance is connected from the above diagram?
Between output and source.
Just tell me the nodes in the from the bottom picture, that between which two nodes I should connect that C1. I just wanted to check that if you have understood this correctly or not. Drain and gate. Yes, but I want the answer in terms of ABCD.
From C to
So what is C? Which terminal is C?
C is source, and drain
C
D
C
from D.
C is basically this terminal. Why are you seeing source?
Okay.
This is your gate, right?
Uh,
What PMOS is doing? PMOS is multiplying its GM to Vs minus Vg. The negative terminal is gate, right? So this capacitance is connected between this. This is your C1. Now do you see? This is your D node or the output node. Is that okay?
yes, sir. Okay.
So if a capacitance is connected between input and output, what do we call that? It is the Miller capacitance of the circuit, okay? And what is the purpose of Miller capacitance, by the way? We have touched upon this in the previous sessions, right?
Yes, sir.
So Miller capacitance allows you to, so I can write this thing. So this is C11, let's say, and this will be your C12, and some, let's say, some output resistance of the PMOS. So this is your V out, and this node voltage is nothing but your V out 1, and this is your V out 2. So this Miller capacitance can be broken into these two capacitances, right?
Yes, sir.
So what do you think this should do? So if you see the transfer function, or let's say V out by V1 minus V2 in dB scale and omega in log scale, so you will see that it will have a DC gain, then it will encounter its first pole, and then it will encounter its second pole. 0 dB per decade, minus 20 dB per decade, and then after the second pole it will be minus 40 dB per decade, okay? So let's say this is the location of your P2, and this is the location of your P1. So 2 sessions earlier I have mentioned that by controlling this capacitance, you can basically control the location of your P1 and P2. So what do you ideally want? Do you want this to be closer or far apart? Just from the basic understanding I want to know. So what will happen if they are far apart, and what will happen if they are closer?
If they are closer, then slope will be large, and
So basically what is happening that your gain is dropping, right? Your this gain of the amplifier is dropping as you go along, right? So you want what? You want to increase the operating range of your device so that you can keep your gain intact.
Yes, sir.
So basically what you want to do, you want to push your P2 at a higher frequency, okay?
Okay.
And that is achieved by adjusting this Miller capacitance, okay? So I
Okay.
can go into much more in-depth analysis of this, but assuming that you guys are advanced UG students, so I am not going into those analysis because those are high frequency circuit stuffs. If you know this much and if you know how to write the transfer function of this block, it will be pretty easy for you to understand that how this P1 and P, what are the values of this P1 and P2, and how by changing C1 you can push the P1 and P2 apart from each other. So what is happening? Because at this point, can you tell me what is this point? What is this point called? This point. What is this frequency called? This is called omega t. What is this?
Sir,
So what is this value, by the way? This line, this is 0 dB, right?
yes, sir.
0 dB corresponds to what value in absolute scale? So what is dB, by the way? V out by V in 20 log of that. That is your gain in dB. So I asked you that this is 0. So what is V out by V in absolute scale?
1.
So beyond this point means right side to this point, what is your gain? Greater than 1 or less than 1?
And greater equal to 1.
Beyond this point, right side to this point. Let's say you have let's say I am taking this point, okay? So that is negative of some dB, let's say minus 2 dB. So if I convert that minus 2 dB in absolute scale, I will have a greater than 1 gain or less than 1 gain.
Less than 1 gain.
So that is as good as I do not have any amplification, right?
Yes, sir.
So what do I want? I want to push my this frequency is called, by the way, unity gain frequency, okay?
Yes, sir.
This is called unity gain frequency because at this frequency your Bode magnitude plot is crossing the 0 dB line. That means your gain is unity. So I want to push my unity gain frequency to a higher value. Why do I want to do that? Because then I can operate at a higher frequency. Is that understood?
Yes, sir.
So that is why this Miller capacitance is used in the first place between two stages. This is the DC picture. And this Miller capacitance, or this is also called Miller compensation. When you read your analog IC design, you will come across this block, okay? This is just an introduction so that whenever you encounter this in your future courses, it should not be a surprise to you that this capacitance is called Miller capacitance and the purpose of this is to split the poles apart. In those courses, you will get to learn that how these things are happening and what are the trade-offs with by doing if I do this, what are the other conditions where I am sacrificing, right?
Yes, sir.
Okay. So now the question, so far we have discussed about what is the purpose of this block. We have understood that the purpose of this block is to, it is nothing but an op amp, right? One
Yes, sir.
stage gives me certain gain, another stage gives me certain gain. So in cascade, the gains will double up. So purpose of a two-stage op amp is, first thing, I want a single stage may not provide me sufficient gain that I require. So I may need to put another stage in cascade. Second thing is that the first stage, whatever the bandwidth it is giving, may not be sufficient to me. Okay, so I can
Yes,
compensate that using a second stage, and I can use that bandwidth compensation also via Miller compensation. So it is again going back to the same thing, gain and bandwidth trade-off. Okay,
yes, sir.
so given this, now the question asks that what are the current mirror, what are the pair of MOSFETs that creates the current mirrors. So can you easily identify that what MOSFET pairs are consisting of current mirrors? MOSFETs are numbered, right?
Yes, sir. 3 and 7.
Uh,
8 and 7.
okay, let me just write down current mirror pairs. So 8 and 7, 8, M8 and M7. Okay.
And 3, 4, 5, 6.
What about M9?
M9.
M9 should also be a current mirror, right?
Yes, sir.
This is I0, we have explained, right? This is also I0. Do you see that M8, M7 and M9 are part of the same current mirror? So in a current mirror circuit, what do you do? Let's say you have a current mirror like this. This is your current source and you have just copied it. Now you can make multiple current sources out of it, right? You can make one at this point. So this becomes your one current source. Similarly, if you connect it to other circuits gate, so it will create another current source. So that is what is happening here. This is your M8, this is your M7 and this is your M9. So these all are the current source, same MOSFET pair that is creating the current source. And what about other pairs? Can you identify other pairs?
Other two of differential amplifier. M3 and
That is
M4.
your M3 and M4 and again
M5 and
M5
M6.
and M6. Okay, so these are the current mirror pairs. So what are the options we have? M9 and M10. No, this M9 and M10 are not current mirrors. This is acting as an active load to this common source amplifier, right?
Yes, sir.
And then this is a current mirror, this is a current mirror, and this thing is a current mirror. So M7, M8, M9 is correct. M1 and M2, M1 and M2 is not current mirror. They are the differential pair. By the way, can you tell me if you remember it? I just want to know if you remember it from our last discussion. What is M1 and M2 doing, by the way? What is M1 to M2? What is M1 and M2 to each other,
Sir, it provides a difference V1 minus V2.
right? But what does it, what is it doing basically? We have analyzed this in detail in the last session, right?
Yes, sir.
So do you remember that? So if I take this as an amplifier, common source amplifier, what is this to this? It is nothing but a buffer, right?
Yes, sir.
We have seen this, right? Why buffer is required.
Yes, sir.
So this entire stuff is nothing but a
Buffer.
gain 1 buffer. And why did we need that? We have explained it that the previous, from where this V1 and V2 is coming, that source may not have a low enough output resistance. So we want our input resistances looking into this and this to be infinity, or
Yes.
ideally infinity, right? So that is why we have used buffers. So you should not forget these things, that what is M1 and M2 to each other, what is M3 to M1, why we have connected M4, and why we have connected M5, M6, and then what is the purpose of M7 and M8, right? The second
Yes.
part I understood that this is new to you, but this part we have studied, right?
Yes, sir.
So please do not forget these things because these are very important. So M1 and M2 are not current mirror. What about M3 and M5? What is the connection of M3 and M5? So these are amplifier buffer pair, okay? M9 and M10, again M10 is M9 is active load to M10. These are current mirror, right? What is M3 to, what is M5 to M3? What is it? What is that connection called?
M5 to M3.
This and this, or for that matter M4 to M6. What is this connection called? And why is this used? Can anyone comment? Exactly, that is your cascode, right? So why do we use cascode, by the way? What is the first reason of using cascode? These things I had explained, right? It is not good that you are forgetting. So what is this? This is a common source amplifier, right? So what, let's say this is
Instead of
your,
register, we use cascode.
instead of,
Register.
why?
Uh,
What is the gain of this circuit? Minus GM time R out parallel, the device R out.
yes, sir. Both resistance. If we use MOSFET, then R not and the MOSFET R not two are comparable, but R and R not is not comparable. If we use
That is
resistance.
what you are telling from the book, right? But you need to understand what is happening. You need, so gain has two products, right? One is this, one is this. So I can increase the gain by what? I can increase this or I can increase this by increasing GM. How do I increase GM? How do I increase GM of a amplifier?
Uh, by increasing anything mu naught COX and
Mu naught COX, those are process parameters, right? What
yes,
is the
sir.
design parameter you have? That is not in your hand as an IC designer. As an IC designer, you have only two things in your hand. That is your W and that is your L. The width of the transistor and the length of the transistor. channel length and channel width. Okay.
Okay.
So by increasing W by L, you can increase your GM. But what is the penalty in that? Your capacitances also increases, right?
Yes, sir.
So it makes your system or circuit sluggish
Yes,
because
sir.
you need more time to charge the capacitance.
Yes, sir.
Okay. Your high frequency performance or the high speed performance degrades. So what do? You target this fellow. Are not parallel the intrinsic output resistance of the MOSFET. How do you increase that? You increase that by increasing by connecting it as an active load, right? You connect another thing. So that is the increasing gain by increasing effective R out or R load. That is the purpose of entire that is the entire purpose of using your cascode. Okay. But
Yes,
then you
sir.
need to be cautious about what is your voltage swings. Okay. So can any one of you tell me which year you are right now in UG and why are you attending this course for gate purpose or anything else? Anyone? I just want to know if you are UG, PG or which year in UG. I want to get into something, so that is why I am asking these things. So depending on the answer, I'll just suggest you something different. So can you please tell me which year you are from? UG, PG. UG means undergraduate, BTech. PG means you are doing MTech or PhD. You can unmute and tell. Okay, so if you are not willing to answer that, let me just suggest it from myself only. Please go through analog circuit design courses from NPTEL by one is Professor Imon Mondal. He is from your IIT Kanpur, and else you can see Professor Nagendra Krishnapura. Okay, so that is IIT Madras. So the details of this circuit analysis and what is what, how your transistors are behaving, if you are looking at your source, what should be the resistance, how your things are connected, you should get a clear idea about that from these courses. Okay, so it is not possible for me to cover everything in this discussion sessions. So you can just follow, you can just type it in your YouTube and you can get the entire course for free. Okay, so it is a suggestion. that along with this course, if you try to deepen your understanding of analog circuits, so you should follow these two courses. Okay, is that fine?
Yes, sir.
Okay, so let's move on. So find the time constant of the circuit shown below. So how do you find time constant for, by the way, what is the order of the circuit? And what do we mean by order of the circuit? What is
Can
the
we
order of
say
this? Yeah, go on.
can we say the number of storage device is equal to order of the circuit?
No, that is partially correct. Number of independent storage element. Don't ever forget that word independent, okay?
Okay.
Why I am telling you? Because I can break this capacitance and add it in parallel, right? Let's say this is CS1, this is CS2. What will you call that then? Will it be a second order system?
No, C1 C2 is parallel C1 plus C2.
Exactly. So independently controlled storage elements, okay? So number of independent storage elements. In this case, we see that it is straightforward one. So it is a first order system. Fine.
Yes, sir.
Another way, number of poles in the transfer function. Can we say that?
Yes, sir.
From your control system, if you remember, that
Yes, sir.
number
Number
of
of
poles in a
poles.
transfer function determines the order of the system.
Yes, sir.
Can you tell me why? Do you remember your linear algebra, eigenvalues?
Yes. Little
What
bit.
is that eigenvalue basically? The characteristics equation.
Uh, Eigenvalue,
If you are
some
given a
matrix lambda
matrix,
into
yeah.
y is equal to lambda into some matrix, then the lambda is the eigenvalue of
So
that
have you
category.
pondered about that? Why, what are those eigenvalues? So those eigenvalues are basically your poles of the system, right?
आइगन वैल्यू का सर कोई रेफरेंस बता दे, कम्युनिकेशन में बहुत ज़्यादा दिक्कत होता है इसके चलते।
So eigenvalue, see, you should treat the eigenvalue as your correct. First thing, whatever you have said is wrong, that it is not a matrix, a square matrix. First condition, okay?
यस सर।
The dimension of the rows and columns have to be same. Then you derive the characteristics equation by whatever the method you have said, that a minus lambda is equal to 0. That is what? That is your characteristics equation. So if you write the, you have heard about this, right? Nodal matrices. Basically your V is equal to Z of I, or I is equal to
वी पी
Y times
एस,
of
यस सर,
V.
नेटवर्क में।
So these are your matrices, right?
यस सर।
Basically this is the representation of your linear system. Okay.
ओके।
So if you just solve this, characteristics of the system is defined by, if you just solve the matrices and find out the eigenvalues, it will give you the exact pole locations, or this will be the denominator of your transfer function. Denominator of your transfer function equal to 0 gives you the characteristics equation of the system. So basically your h of s will be, let's say, some n of s divided by d of s. Okay, so your d of s equal to 0. The solution of this equation gives you basically poles. Okay,
Okay.
so these are the same thing. If you solve it in this domain, z and z impedance or admittance domain, and find out the solution, will give you the eigenvalues.
Okay.
So this is nothing but the values that determines the characteristics of the system. Means if your system is oscillatory or not, damped or not. Okay,
Yes, sir.
so for a first order system, what is the ideal form of the transfer function? I should have one pole, I should have 1 0, let's say 1, and I should have some DC gain, right?
Yes, sir.
So this is the form of general transfer function for any first order system. I
Yes,
can
sir.
have more than 1 zeros also, right?
Yes, sir.
So why A0 is your DC gain? How can I say A0 is your DC gain?
Put S is equal to 0, then A0 is there only. So that
Exactly, just I wanted to check, right? H of 0 is your A0. So this is also, if you notice, that this is the uh, beauty of writing this equation in this form. I am not writing it as S plus Z1 by S plus P1, right?
yes, sir.
So your pole locations P1 is corresponding to time constant of your first order circuit. So can you tell me directly that what is the time constant, what is the relation between time constant and pole? What is the unit of pole?
I don't know.
So when I have, what is the unit of omega?
It is frequency. It might be hertz.
Omega is hertz. Omega
नहीं
is
पता.
equal to 2 pi f, right? What is the unit of f? F is unit is hertz or 1 over second. And what is the unit of this?
Radian.
So what is the unit of omega?
Radian hertz.
Radian per second, right?
Yes, sir. Radian per second. So,
So unit of pole is radian per second. So what about tau 1?
and tau is radian. Sorry, and tau is second. Inversely proportional. Both are inversely. Relation is inverse.
So now
Uh,
what you need to do, you just need to find out the transfer function. Can you immediately tell me what is the transfer function? It is the gain, right? It will be Rp over Rp plus Rs plus 1 over SCS. Is that okay?
yes, sir.
It is just a resistive divider, right?
Yes, sir.
So what will you have? You have SCS times RP, and that is divided by S RP plus RS times CS plus 1. So your H of S has the form of S times CS RP over RP plus RS times CS plus 1. So can you tell me how does this look like in Bode plot? At S equal to 0, what is your output?
0.
And at S equal to infinity?
CPRP by CP plus RPCS.
CP is not there, it is CSRP. There is no CP, right? CSRP
Yes.
by RP plus
RP
RS times
into C.
CS.
Yes, sir.
That is your RP over RP plus RS. And this is the location of your pole. And what is the value of your pole? 1 over CS times RP plus RS.
Yes, sir.
1 over time constant. So what is your time constant?
CS into RP plus RS.
So that value you can calculate, right?
Yes.
So value will be what? Your RS plus RP is 6 and times 3. So it is 3 picofarad times 6 kilo ohm. So 18, what is the answer? 18 watt second. This is 10 raised to minus 12. This is 10 raised to 3. So it will be 10 raised to minus 9. That means nanosecond, right?
Nanosecond. Yes, sir.
So by the way, looking at the circuit, did you understood that it is a high pass filter
Yes,
basically?
sir. Yes, sir.
So can you tell me how?
Because
By looking at the circuit. So how do you check if your circuit is a high pass filter or low pass filter? Output across resistor. I did not get that. Means how, what is the flow? What is the flow of and finding what kind of filter is this? You start at zero frequency, right? And you keep increasing your frequency and you see what is the output. So when you have zero frequency, this capacitor is open. So what is coming out at V0? Nothing is coming out at V0. So what will be your V0? V0 is 0. Basically input is not traveling to output. So at lower frequencies, for example, at S equal to 0, whatever input you apply to the to this side, nothing is coming out at V out. So it is blocking the low frequency signals. As soon as you are increasing your frequency, for example, at very high frequency, at infinite frequency, this will be acting as a short. So it will be what? It will be just nothing but a resistive divider. So it will pass a certain value of the signal depending upon the ratio of these two. That is what is happening, right? This value is what? This value is your Rp over Rp plus Rs. So from the circuit itself, you can see that it is a high pass filter. Okay. So there is many way to understand these things. You can analyze the entire thing in time domain also. You can just solve a first order differential equation and found that T over tau, that tau value is your Rs plus Rp times Cs. But in this course, you learn how to read the Bode plots, okay, and how to deal with the poles and zeros of the circuits. So far, is this clear?
Yes, sir.
So if I move on to the next problem, can you tell me what is the order of this circuit?
Sir, it is looking like second order.
So looking like second order, okay? Looks can be deceptive, right?
Yes,
We'll
sir.
see. So if you are not sure, what will you do? You find the transfer function and see the denominator and factorize it. You will see that what is the order of that equation. So what is your V out by V out of S divided by V in of S? By the way, what is this S?
सर ये फ्रीक्वेंसी डोमेन लैपलास वाला ऐसे.
It is Laplace transform, right?
यस सर.
So what is Laplace transform?
एफ टी टू द पावर माइनस एस टी.
Sorry, if I write this x of t, what is that? You have mentioned this, right?
यस सर.
So do you know what is this basically? Means what operator is this? It comes from something called your Heaviside operator, okay? Just to let you know that Laplace transform is a special case of Heaviside operator and your Fourier transform is a special case of Laplace transform. Do you agree with that statement? Just put S equals to sigma plus j omega and put sigma equal to 0. That will give you your Fourier transform.
यस सर.
So Laplace transform is more general, right?
यस सर.
And here we do not have to encounter that j or whatever I, whatever you call, depending upon if you are a mathematician or a physicist. So it becomes it makes the life easier for the beginners to handle this Laplace transform. So now if you do that, so
तो
what will
ये एच
happen?
ऑपरेटर क्या होता है?
Sorry,
व्हाट इज दिस एच ऑपरेटर?
this is called Heaviside operator.
ये पढ़ना होता है इन यूजी लेवल.
Just to let you know, so that if you encounter this terminology in future, you just don't get a shock that, oh, it is something new, I have to learn everything new. So remember that whenever you encounter Heaviside operator, just remember that somebody had told you that it is nothing but a more generalized form of your Laplace transform. So Laplace transform you know, right? So
यस सर.
then reading that new concept will become easier for you. So that's why I keep mentioning some advanced stuffs. I know that those are not required for you at this moment, but whenever you face those terminology in future for the first time, it will appear like something you can achieve very easily or conquer very easily. Okay.
यस सर.
So that is the purpose. So what is the transfer function? R2 plus 1 over SC2 divided by R2 plus 1 over SC2 plus R1 plus 1 over SC1. Is that okay?
Yes, sir.
So then let us simplify that. So S C2R2 plus 1 divided by S C2R2 plus 1 plus this divided by, okay, let us write it in this way then. This will be more convenient. R1 plus R2 times S square C1 C2 plus this is C1 or SC1, or let's say C1 SC2, and you have SC1 times SC2, and in this case you had 1 over SC2. So this SC2 gets cancelled. So you have SC1 times 1 plus SC2R2, and that is divided by, if you take S common, so it will be SC1C2 times R1 plus R2 plus C1 plus C2. So this S gets cancelled. So it will be your C1 times 1 plus SC2R2 divided by S times C1 C2 R1 plus R2 plus C1 plus C2. Is that fine?
Yes, sir.
So what is the order of the circuit? First of all, tell me how many poles and zeros are there? How many poles and how many zeros?
Sir, one
What is the value of the zero?
0.
Come on,
A
yeah. What is the value of
pole at 0 and uh, 0 is equal to
pole at zero? Are you sure?
sir लग पता नहीं sir. No sir. No sir.
So what is the location of the zero? First tell me that. It is minus 1 over R2C2, right?
Yes sir.
What is the location of the pole? C1 plus C2 divided by C1 C2 times R1 plus R2 with a minus sign.
Yes sir.
Is that okay?
Yes sir. Okay.
So what is the order of the circuit now?
Sir 1.
So looks are deceptive, right? So
Yes
order of
sir.
the circuit is 1. So what is the transfer function then? It seems like this is the transfer function, right? S C1 C2 R1 plus R2 C1 plus C2 C1 and then C1 S C2 R2 C1 C1 C2 S R2. Okay.
Sir.
So what is the significance of this minus sign? If we are at it, let us discuss this also. What is the significance of these minus signs?
Minus sign.
Okay, I know that you will remember it immediately if I draw it in a different plane.
Sir, I think something is going into that.
Okay, just tell me this much. So if I write here sigma and here j omega, what is this plane? This is called S plane.
Yes,
Remember this from your control system course?
sir. I think you are talking about stability. Pole is in.
Obviously, right?
Yes, sir.
So you have a left hand side pole here.
Yes, sir.
So that means your system is
Stable.
exactly. So what does the real pole mean basically? Real pole mean that at this location you have a decaying system.
Yes, sir.
And what
E to
about
the power
a
minus
and what about this thing?
increasing e to the power 80.
It is increasing, right?
Yes, sir.
And what about at this location?
That location. If above that in imaginary axis it is sinusoidal oscillating,
If
but at the
imaginary
machine I
axis
don't know.
in imaginary axis I will have a
Oscillatory
I will
sinusoidal.
I will have what? I will have a sinusoidal, right?
Yes, sir.
So this is this right? What is a
Yes, sir.
transfer function like this? What does this represent?
It is at pole single.
At pole at zero location, right? Is equal to
Yes,
zero.
yes, sir.
So what does that mean? That means a pole at origin. What does that mean? What is this?
पता नहीं sir.
This is an integrator, right?
Yes,
Isn't it? It is an ideal integrator. So if your delta is your impulse response, if delta t is your impulse response, and if your system has this, so what is you will get? You will get a unit step.
yes, sir.
And what about if I have a pole at these locations? How will that look like?
Uh, it will be exponentially decaying with a sink-like function.
It will be like this, right? Decaying sinusoid, decayed oscillation.
Yes, sir.
And
Decay oscillation.
similarly, at this place, it will be increasing oscillation, right?
Yes, sir.
So in this side, system is unstable.
Unstable.
Here, system is stable. And at this line, what is the condition? What do we call it?
Marginally stable.
Exactly, marginally stable, right?
Yes, sir.
So these things you should remember always, okay? Whenever you are seeing any transfer function, you always remember that as this is a first order circuit, it is ultimately an RC circuit, right? Either the capacitor will charge or the capacitor will discharge. So when you do not have any external input and you let the system relax, so obviously the capacitors will discharge. And how does discharge of an capacitor look like? It look like something like this.
Yes, sir.
That means your system is stable, right? There is no oscillation. It will be something like to the power minus x or at, isn't it?
Yes, sir.
And this will translate to your in Laplace transform. If you do, it will be 1 plus s plus a. That is what you are getting here.
Yes, sir.
So try to correlate these things in your mind whenever you are studying. You have been taught control system for a particular reason. Okay.
Yes, sir.
Okay. So let's move on. Okay. So now they have asked that find the open
Sir,
circuit. Yeah.
sir, in previous condition, why, sir, C1, C2 are independent or dependent? How can we analyze that?
In this case, you see that your C1 and C2 are dependent, right?
Yes, sir.
That is how you want to know how intuitively you can analyze that.
Yes, sir.
Okay, then think it in this way that whenever, let's say, these are the two terminals, looking into this, you want to find the output impedance, okay? How will you do that?
Sort sort the V out.
Short the V output impedance. Short the independent sources. What is the independent source here? This is the independent source,
Yes,
right?
yes,
So don't this come into series?
yes. They will come in series.
So that is, so what is the series capacitance?
C1 by C1 plus 1 by C2.
Series capacitance is C1 C2 by C1 plus
C1,
C2.
yes,
And what is your resistance?
R1 plus R2.
What is your pole location should be, or time constant should be?
Okay.
You see, that is what you are getting.
Yes,
You see the intuitive analysis. This I did not want to bring out here because in some circuit you may not be that much familiar with this analysis at this moment, so you may commit mistakes, okay? But as you have
yes,
asked, so I have told you that how to look into this thing. You can directly, just like that, you can write the transfer function. I have derived it because you need to know the steps. Once you start to look into or understand the intricacies of the transfer functions, you should be able to directly write it in this form. This is the form that is mostly preferred for
okay.
low pass kind of scenarios. Okay, you are a UG student, right?
Yes,
Okay, so I would have recommended another lecture series, but let's just skip for that. Let us wait for when you go into your PG, contact me. I'll share with you another lecture series where you can find this detailed analysis so beautiful that you will not find it in any books. Okay,
yes.
so you see,
सर
right?
पीजी कांटेक्ट कैसे करेंगे?
Sorry.
कांटेक्ट how I will contact to you?
So you have my email address, right?
Yes, sir.
So I am not sure if you guys have my email address. Just drop me a mail with your doubts and anything what you require, any information. If that is permitted from my side, I will share it with you. There is no doubt. Okay.
Yes, sir.
So this is what it is. Now let us delve into find the open circuit time constant and short circuit time constant of the network shown below. So do you know that this has been taught in the class? Have you gone
Sir,
through the lecture series?
no, sir.
Okay. So the book where it was referred from was from Donald Nieman. Okay, not the semiconductor physics book you generally study, but it is another book called Microelectronics Circuits. Okay, Microelectronic Circuit Design from the same guy, Donald Nieman from New Mexico University. So what you can do is that start it in this fashion. Okay, let's say this is a resistance and this is a resistance. Okay. Let us take only this circuit. This is CS, this is RP, and this is your V out, and this is your V in. So can you tell me at S equal to 0, what will be your V out? At S equal to 0, from the intuitive analysis what we have done earlier, can you tell me at S equal to 0 or DC what will be your V out? It should be straightforward, right? What is the condition on the capacitance CS at S equal to 0? At S equal to 0, your CS is open, right? That means your V out is 0. At S equal to infinity, CS short, your V out is RP by RS plus RP times V in. So how does your Bode magnitude plot look like? It looks like something like this. Something like of a high pass response, right? And what
Yes,
is
sir.
this pole? This pole is called your open circuit pole, okay? P open. Why it is called open? Because around this frequency, because if you have this CS open, you will get a open circuit at the output. That means input and output are not connected. So this CS corresponds to your open circuit pole. It is named in that convention, or they are called it 1 over tau s. So what is tau s? Can you quickly tell me what is tau s from the circuit? Tau s will be what?
RP
Capacitance
by
looking into these terminals. The capacitance is CS and resistance looking into this terminal. What is across the capacitance? So this will be shorted. So what is your tau s? CS times what is R
uh,
equivalent?
R1 plus R2.
RS plus RP. Now consider another case. CP, this is RP and this is RS. This is your V in, this is your V out. So at S equal to 0, what is your V out? What is the condition on CP? It will be open, right?
Yes, sir.
So your V out will be,
RP. RP divided by RS plus RP.
and what about at S equal to 0? S equal to infinity?
Uh, That that is sorted RS.
No, no. How can it be voltage can be equal to RS?
V in times RS.
Why V in times RS? What is V out? V out is the difference between these 2 points, right? If this is shorted, that means what? What is the difference of potential difference of V out?
So
If
no
this is
potential, sorted
so that means
zero.
your V out is zero, right?
Yes, sir.
So how will that look like?
Yes. And a constant and then goes to zero.
This is your low pass filter kind of response, right?
Yes, sir.
So let's say this one was your P0. Let us name it PS or P short, PSH. So why this is called short? Because this nulling of this capacitance is giving you a short circuit at the output. So what is PSH? It will be 1 over tau SH, or let's say tau P. They call it tau P, the short circuit time constant. Can you immediately tell me what is it? Short circuit time constant by looking at this circuit. What is the capacitance? It will be something RC, right? Some R times some C. What is the C here?
CP,
What is the R here? How to find out R?
RP, uh,
RP.
in parallel with RS.
How did you say that? Because you have just nulled your
V
independent
in,
source and found out the Thevenin resistance looking across this capacitance, right?
yes, sir.
That is how you find your Thevenin resistance. So this is your CP times RP parallel RS. So now if I put these two circuits in cascade, or in other terms, now let's say this is your CP, this is RP, this is CS, this is RS. So immediately I can see that I have two possibilities. When my PSH is greater than P0, that will depend upon the value and of resistances and capacitances. How will that look like? What was this? This was something like this. And my another curve was something like this. So my resultant curve will look like this, right? So I
Yes,
have
sir.
one pole here, and what is this pole? This is P0. And what is this pole? This is PSH, right? So this kind of transfer function is called band pass, right? Is it okay? So this corresponds to your F low and this corresponds to F high, and this gives you the bandwidth. This we have discussed earlier, right?
Yes, sir.
Now what if my, because I do not know the numerical value of PSH and P0 as of now. What if your P0 less than PSH? Then your rate curve will be something like this, and this is your P0, and somewhere here you will have your PSH. Let's say this is your PSH. So what kind of response you will get? What is this thing called? Band reject or band stop or notch filter, right?
Yes, sir.
So depending upon the value of P0 and PSH, this entire thing can be used as BPF or BSF, band pass filter or band stop filter. Okay.
Yes, sir.
Now in this question, they have asked us to find out the value of open circuit and short circuit time constant. So what was my open circuit time constant? TS. TS was CS times
RS plus
RS
R.
plus RP. And what is that? CS is what? 2. RS plus RP is 7. So it will be
Yes,
14 nanosecond.
yes, sir.
And what is your tau P? Tau P was CP times RS parallel RP, right?
Yes,
CP is
sir.
what? CP is 4 times 5 parallel 2. That means what? 10 over
10 by
7
7.
nanosecond.
Yes, sir.
So if you do this, it will be for 5 point. So I should write this small s. What is the difference between small s and capital S?
Small
In
s is time
say,
and
say,
capital S is Laplace domain.
no. Capital S
Siemens.
Laplace is also small s.
Oh,
Capital S determines Siemens, right?
yes, sir.
MHO, Mo.
Yes, sir.
So
Siemens.
I should write always small s. Okay, remember this thing. So this is your right answer. Now a follow-up question to this is that they want us same thing. Your RS is 5 kilo ohm. Just let us confirm. RS is 5 kilo ohm. Yes. RP is 2 kilo ohm. CS is your 2 picofarad and that is your 4 picofarad. 4 picofarad. Okay. So they want to find us the bandwidth of the network. So bandwidth is, we obviously know it will be FH minus FL. So what is FH? 1 over tau H minus 1 over tau L. So tau H will be which one? That one. So tau H will be lower one or the higher one?
Sir, low.
So it will be 1 over your 5.71 nanosecond, right? Minus 1 over your 14 nanosecond. So your 1 over 5.71 minus 1 over 14 will give you 0.103 into 10 raised to 9 radian per second. Now I need it in terms of hertz, right? So I have to divide it by what?
Um, 2 pi.
Divide it by 2 pi, right? So
Yes,
that
sir.
is equivalent to, if you divide this by, so bandwidth in hertz will be that divided by 2 pi is this hertz. So that is 16 megahertz. Okay.
Yes, sir.
So around this will be your correct answer. So tell me if you have not understood anything till now, else I'll move on.
Sir, move.
Okay. So due to Miller effect, common source amplifier have a input capacitance and dash cutoff frequency. Okay, so let's say this is the gain in dB and this is omega in log. Okay,
Yes, sir.
so your common source amplifier has frequency characteristics something like this. This is your omega L or P1. This is your omega H or P2, pole location 2. So if you remember what determines these poles and what determines this pole. So if I draw the common source amplifier,
One coupling capacitor determine and one
so coupling capacitor determines what?
one pole.
So what pole that will determine? So this is all we have. So yeah, coupling capacitors determines the low frequency poles, right? And high frequency pole is determined by your C input basically. That is what? What is your C input? We have calculated it, right? C input
Yes.
will be your CGS plus the Miller amplified version 1 plus mod of A times CGD, because this capacitance is connected between input and output, right? So this is your Miller capacitance. So due to Miller effect, this capacitance will get multifold. Okay.
सर इनपुट कैपेसिटेंस किसको कहते हैं सर एक बार बता दीजिएगा
Okay.
सर सॉरी
Just
सर
no, it's fine. Just let me show you week 8's discussion. We had done it, so I'll
यस सर
just
2 week बिफोर week 6 week
week
7
week 7, right? So this we had done, this CGS, this plot you remember. So input capacitance is what? This you remember, right? This plot, I have drawn the same plot here also. Just look at this thing. So now if I tell you what is input capacitance, okay, I thought I had done that in last class. Okay, so what is the input port? So if I just draw a black box, it is a common source amplifier, right?
यस सर
So let's say this is the system. So this is your gate, this is your source, this is your drain. Here you are probing your output, here you are giving your input, right? Is that fine?
यस सर
Okay. So this is basically your 1 1 dash or port 1. and this is your port 2. Okay.
Yes, sir.
So what is the capacitance you are seeing? You are seeing a capacitance here and another capacitance between these two. This is your CGS, this is your CGD, right?
Yes, sir.
So this CGD can be broken into two parts. One is your 1 plus A times CGD due to Miller effect, and one is, in this case, it will be 1 plus 1 over mod A times CGD.
Yes, sir.
So now if I tell you what is the capacitance you are seeing at the input port, what will you tell me? This is grounded.
Input port, uh,
It
parallel
is a
combination
parallel
of
combination
CGS.
of these two, right? So that
Yes,
is
sir.
what I have written.
In general, we can say by looking through the input, what we encounter, that is the
Yes, that is true, but that is not how it is measured. So you know about S parameters,
S parameters. Sir, we,
scattering parameter, Y parameters you know.
yes, sir. Y parameter, no.
Okay, just listen to the terminology. There is something called vector network analyzer. Okay, just listen to me that it is an measurement equipment which measures the S parameters. Okay, versus frequency. So it measures S parameters or your scattering parameters. So these S parameters, these are also two port parameters. Okay, can be converted to your Y parameters. Fine.
Yes, sir.
Now for a two port network, you know that you have what? Y11, Y12, Y21, Y22, right? Four terms. Two ports you have. One port here, second port here.
Yes, sir.
So by you measure this, convert to this, you know your Y11. So Y11 will obviously have your imaginary part also plus real part also. J times imaginary Y11 plus real part of Y11. Fine.
Okay. Okay. Yes, sir.
So this imaginary part of Y11 divide by 2 pi. So what is imaginary part of Y11? If you have a, let's say this J. So if you have a, let's say capacitance, only if you have a capacitance, what is the Y11 of this capacitance? What is the Y parameter of this capacitance or the admittance? What is Y of this admittance? X is what? X is 1 by j omega c in. Is that clear? X is.
Yes, sir.
So then your Y is what? Or more precisely, Z is this. Y is what? Y is your 1 over that minus j omega c in.
Yes, sir.
So this is what? Minus j omega c in, looking at port 1. So you measured this and now your c in will be imaginary of y11 divided by omega. Okay. So this is how you actually measure the thing, whatever your question was. Because
Yes.
as you go to the high frequency, there will be so many reflections and you will get to learn these things, the interplay of frequency and how you look into this. So whatever you have said is correct, that if you look into the input port, whatever capacitance you should see is the C in. Okay. But that is not how it is measured, because you do not know what is your CGS or CGD. You need to characterize this. Characterization means what is not directly measured, but you measure some quantity and derive the result from that quantity. Okay. So in this case, what you are measuring S parameters or your S11. Convert that to Y11. And that Y11, from that you are getting your C in or the input capacitance. Is that clear?
Yes, sir.
Okay, so that is how it is measured in real life, and whatever the sense you have made, that looking into the input, whatever capacitance you should see, not what you are seeing, you should see, because there will be so many fringing capacitances and everything. Because at high frequency, any two lines, if current is conducting or signal is conducting, that will create a capacitance through the air, because air is also a dielectric, right?
Yes, sir.
Okay, so by default, so due to Miller effect, common source amplifier have input capacitance is increased, right? Because my A is greater than 1. So it has a high input capacitance. Okay.
Yes, sir.
And what did I tell you, that how does the pole appear? Pole appears in a form of GM equivalent times C equivalent. So in this case, if it was determined by C in, so as your C in is more due to Miller effect, so your FH will be what?
Low.
FH will be
Inversely.
low, right? And
Yes.
that also limits your bandwidth.
Yes, sir.
You understood, right? Why I discussed the earlier part, that if you increase your W by L, your
Yes,
CGS
sir.
and CGD will also increase. That will
Yes, sir.
increase your C in, and that will basically push your pole to a lower frequency. But what do we want? We want higher bandwidth. So we want to push this in the right hand side direction. So that is the
So,
interplay between your GM by C in. Okay.
yes,
So
sir.
this will be large, this will be low. So this is what it is. Okay. So a source follower. What is a source follower? What is the other name of source follower?
Common drain.
Common drain, right? So how that is drawn is that you have a some sort of common drain, and later it is not necessary, but let us add some feedback RG. And what, where are you probing your output? At the source, right?
Yes, sir.
Because this is where your input signal is provided, and this is where your
Out.
output is taken, right?
Yes, sir.
So what is the input impedance?
Infinite.
But there is a RG, right? So it will be
RG. Yes,
RG,
sir.
right?
Parallel with infinite.
Parallel infinite, that is open circuit. So I can simply write it is as RG, right?
Yes, sir.
And what is R out?
R out. Uh, GM in parallel with R naught.
So R naught in parallel with 1 over
1 over GM.
GM, right?
Yes, sir.
So what do you think? Which one is higher and which one is lower?
R naught is higher, but it is in parallel with GM
So this is lower and
lower.
this is higher, okay?
Yes,
So
sir.
that is why your common drain acts as an what?
Act as a buffer, source follower.
Act as a buffer, right? So
Yes, sir.
it has almost infinity input impedance and very low
Output impedance.
output impedance. So this helps in removing the loading effect, what we have discussed, right? You
Yes, sir.
remember we repeatedly mentioned that this is what? This is nothing but your common drain or the source follower configuration,
Yes, sir.
right? The purpose of this is to introduce a stage which has unity gain but infinite input impedance and very low output impedance. So this is high, this is low.
Low.
Moving on to this, find the capacitance C out for the common source amplifier shown below. So how do you find out the C out? So you have what? You have something connected to this and you have CDB connected here because your body and source is shorted, right? To zero value for an NMOS. So this is your CGD, this is your CGS. So now with Miller effect, it will be what? Your C out will be what? CDB plus in parallel to that Miller cap, Miller output of CGD. So CDB plus Miller output of CGD is what? Miller output of CGD is 1 plus 1 over that gain times your CGD. We have seen this, right?
Yes,
At
sir.
output it is this. So CDB is what? CDB is your 16 femtofarad. What is femto, by the way? 10 raised to how much?
15, but it
Minus
is
15,
P
right? Minus 15.
minus 15. Yes, sir. Minus 15.
So what is A, by the way?
Again,
So A is what? In this case, gain of the amplifier is what? How much? GM is this. RL is this. So obviously gain is what? Gain is
8.
8 minus 8
Yes,
basically. You take the
yes,
modulus of that and CGD is your 10 femtofarad. So this will be 16 femtofarad plus this is how much? This is 1 plus 1 over 8 is 0.125 times 10 femtofarad. So 16 femtofarad plus 11, yeah, it will be 1.125 times 10 femtofarad. So that will be 27.25 femtofarad. Is that okay?
yes, sir.
Now can you tell me how do you find, how do you measure C out? What are the steps? Connect VNA, measure S parameter, convert to Y parameter, and your C out would be imaginary component of 2 pi f. What is this? Which term of the Y parameter should I look at for finding output resistance? Y11 was giving me C in.
Input. Yes,
So
sir.
output resistance will be given by
2 1 and 2 2. पता नहीं.
C22, right? Exactly, C22, Y22. So you remember your network theory classes, right? What is Y1 and what is Y2? So your I is basically what? Y times V. Is that clear?
Yes, sir.
So your I1 and I2 That is equal to what? Your y11, y12, y21, y22 times v1, v2. So your I1 is equal to what? Y11 times v1 plus y12 times v2. I2 equals to what? Y21 times v1 plus y22 times v2. Fine. Now if you want to find out y22, what is the definition of y22? V2
V2 by I2 when
I2
uh,
by v2 when v1 is equal to 0.
yes, sir.
This 0 means this will go away and this will just become this. Right?
Yes,
So that
yes,
means your excitation is also at the second port, your response is also at the second port. So to find an impedance or R test, what do? You connect the V test at the same port and find out the I test through that. That gives you the input impedance, right? How we have been calculating that?
yes, sir.
It is the same manner. That is why it is Y22, not Y21. Because if it is Y21, then I would have given my response excitation at the V1, another port. That is when we do that, when you want to find out the transfer coefficient. That is
Yes,
why
sir.
it is called transconductance. When I put my input at gate and finding out the output current at Y, output current at drain, another port, okay? So I want to find out the output impedance, means I want to look into output and see what is the capacitance there. That means I have to give the excitation also at the output and find out the response at the output. That is why it will be Y22. So you are right, it is imaginary of Y22 divided by 2 pi f, okay?
Yes, sir.
Okay. Now when a negative feedback is applied to an amplifier, the voltage gain reduces by a factor. So what is a negative feedback? This also we have touched upon in last class, that let's say this is an amplifier and let's say this is the sensor path. So this is your V out, this is your V in, okay? This is plus, this is minus. That is the definition of your negative feedback. Fine.
Yes, sir.
Now can you tell me what is this signal? This is beta times V out. This is V out. This is V out. So this is beta times V out.
Yes, sir.
What is this signal? This is V in minus beta times V out.
Yes, sir.
And this is what? A times V in minus beta times V out.
Yes, sir.
So V out is equal to A times V in minus beta times V out. So what is my V out? V in times,
Uh,
try it,
1 minus beta A.
1 plus beta A.
1 plus beta A. Sorry, sir.
So ideally your gain was what? Ideally your gain was, it should have been. So by the way, this is what? This is called your open loop gain. That means you open the loop and measure out what is your V out. So V out open is equal to what? A times V in.
Yes, sir.
So that is your open loop gain. And this is your A closed is equal to A open divided by 1 plus beta times A open. So your gain has reduced by a factor of 1 plus A beta. So in a closed loop negative feedback system, I gain what?
Gain.
I achieve achieve stability,
uh,
but what do I lose?
gain by a factor of 1 plus beta A.
Exactly. So this you need to remember, okay?
Yes, sir.
Now suppose I want to create oscillation. What should I do?
माइनस की जगह प्लस कर देंगे.
So oscillations require positive feedback, right?
Yes, sir.
Can you give a practical example of positive feedback? Where we use it deliberately?
CRO.
CRO, oscilloscope.
Yes, sir.
But that
Positive.
is just a viewer, right? If you would have told me signal generator, I would immediately accept your answer. CRO is what? CRO is a oscilloscope. It visualizes the signal that is being generated by somewhere else. In modern day CROs, you will have signal generators. Okay. So signal generators are what is generating your signal. Very easy example is the clock signal, what you see in your digital circuits, right?
Yes, sir.
That clock is, do you know how does that clock getting created? Something called phase lock loop that involves positive oscillation. Sorry, positive feedback. Okay. So clocking is an example. Obviously, what you have told that signal generators are also another kinds of example where you have these oscillators. And what one of the nature's way of oscillation is the crystal oscillation. Quartz, right? Quartz crystals are used for oscillations.
Okay.
Find the pole frequency of common source amplifier. I think this you can do yourself or let us tackle it in next class. Okay, so I think that should be enough for today. So please do, the key message was go through these two lectures if you want to really learn what is analog circuits. And believe me, once you spend your time on these two lectures or any one of these lectures, it will be hugely beneficial for you. Your gate problems will be like nothing, piece of cake. Okay, once you understand the concepts that how to actually read analog circuits. Okay,
Yes, sir.
I think that's all for today. Thank you.